So we're going to do Chapter 11, the last chapter in Chem 1A, liquids and solids. The first thing we're going to do is look at the three phases of water: gas or steam, liquid water, and the solid phase of water or ice. It should be very obvious that water in the gaseous form has its molecules very far apart from one another. There are few, if any, attractions between them. The particles are completely free to fly around the container. If the container is closed, if it's open, just fly out. Gases have a very low density. For steam, it's 5.9 times 10 to the minus 4 grams per cubic centimeter. When water is in its liquid form, however, there are temporary attractions between the water particles. They make and break these attractions, and while that provides enough cohesiveness for water to maintain a surface and stay at the bottom of a container, a liquid can still flow because the molecules can slip and slide over each other. The density is much greater than a gas, almost 1 gram per cubic centimeter. And finally, we get to solid water or ice, and very strange phenomenon. Ice has a lower density than liquid water, and that's very rare. Most substances, the solid is more dense than the liquid, but not water. The solid is less dense than the water. This is a good thing because it helps life to be possible on Earth. And in the molecular view, the particles of water are locked in a crystal pattern. In the case of water, it's a hexagonal crystal pattern. Molecules are no longer free to move about, although they can stay in place and vibrate. So there are the three phases of matter, and from just this discussion, you should see that it's the attractions between particles that really are very important in determining the phase properties of a substance. We've talked about intramolecular bonding already in Chapter 9. That's the bonding between atoms in a single molecule. In a water molecule, you have an intramolecular bond between hydrogen and oxygen, a covalent bond, if you will. But that's not really the bond that we're talking about as a determining factor for the phases of a substance and the physical properties. It's the intermolecular bonding. And by intermolecular bonding, we mean the attractions between particles. It's almost always a much weaker attraction than intramolecular bonding. And it's this kind of attraction that affects so greatly the physical properties of water, its boiling point, its melting point, etc. Now, we all know that many liquids and solids have an odor. And if you think about it, that odor is caused by particles of that substance outgassing or vaporizing. The rate of emission from the solid or liquid depends on temperature and the strength of the attractive forces between the particles. And the vapor particles, like any gaseous particles, collide with container walls and they cause a pressure. So we call that pressure vapor pressure. Imagine you've got some water molecules at the bottom of a beaker or a flask and you put a stopper in it. Some of the water molecules at the surface have enough energy to make the jump into the vapor phase. And as they begin to accumulate in the vapor phase, some of them begin to collide with the liquid and be recaptured by the liquid. Eventually, we get to a point where the water particles are evaporating at the same rate that they're condensing back into the liquid. And that is a dynamic equilibrium. Now, of course, if you don't have a top on, then the particles will just leave and the substance will eventually evaporate. But if there is a stopper there and the particles can't escape to the environment, then this kind of dynamic equilibrium will be established.
A liquid confined to a cylinder, as shown here, with no other substances present, exerts a vapor pressure in the space above it. Molecules continuously transfer back and forth between the gas and liquid phases. The gas pressure in the cylinder represents the vapor pressure of the liquid that results from this equilibrium. As the temperature of the cylinder increases, the average kinetic energy of the molecules increases in both the liquid and gas phases. A higher average kinetic energy facilitates the escape of molecules from the liquid phase into the gas phase. At the same time, the rate of return of gas phase molecules to the liquid also increases. A new equilibrium point is reached at a higher gaseous vapor pressure. The increase in vapor pressure with temperature is exponential. In this equation, A and B are constants that differ from one liquid to another. The absolute temperature is expressed in kelvins. When we take the natural log of both sides, we obtain this equation. It tells us that a graph of log vapor pressure versus the reciprocal of the absolute temperature should be a straight line.
So here's a question that I'm going to ask you in class. You have two flasks. One of them has 5 grams of water in it and a stopper. The other has 10 grams of water in it and is stoppered. We know the container with 5 grams has a vapor pressure of 17.5 torr. So the question is, what's the vapor pressure in the flask with 10 grams of water? So think about that, and we'll be asking you that in class. Now, we've talked about the Boltzmann distribution before, and once again, let's review it. That at any given temperature, you have a whole distribution of kinetic energy. Some particles have very little kinetic energy. Some particles have a lot of kinetic energy. Most of them are near the average right here. And at a lower temperature, the curve is higher. At a higher temperature, the curve is lower and more broad. Now let's say that this is a threshold kinetic energy that a particle has to have to break the attractions that are holding it in the liquid phase and evaporate. It has to have this minimum kinetic energy. So do you see what happens when we raise the temperature? It's all the area under the curve that relates to the number of particles that have the requisite energy. And you can see that at the higher temperature, many more particles have the energy required to evaporate. So only a small fraction of the molecules in a liquid have enough energy to escape, but as the temperature increases, the fraction of the molecules with escape energy increases. The higher the temperature, the faster the rate of evaporation. Now, if we plot vapor pressure versus temperature of various liquids, we see these curves. Dimethyl ether, which has a very high vapor pressure, at 20 degrees C, its vapor pressure is a little less than 500 torr, and very quickly gets to 760 torr by heating it just a little bit. 760 torr is atmospheric pressure, and that's where boiling begins. So it has a very low boiling point, diethyl ether does. Now, what about ethanol? Ethanol has a much lower vapor pressure, around 50 torr at 20 degrees Celsius. So it takes quite a bit more energy to get its vapor pressure up to 760 torr, and it will start boiling at 78.5 degrees Celsius. Water, of course, has an even lower vapor pressure at 20 degrees C. So it has an even higher boiling point. The higher the vapor pressure at a given temperature, in other words, the lower the boiling point will be. Now, as we mentioned before, when the temperature of a liquid reaches a point where its vapor pressure is the same as the external pressure, vapor bubbles can form anywhere in the liquid, not just at the surface. They can form underneath the surface at the boiling point. And so this phenomena is what we call boiling. And the temperature required to have the vapor pressure equal the external pressure is called the boiling point. Now, usually that external pressure is taken at standard conditions, meaning 1 atmosphere or 760 torr. But what would happen if we reduced the pressure on a liquid? Could we get the liquid to boil at a lower temperature than it does at normal atmospheric pressure? Let's watch this video.
Can this water boil without heating it? Well, it can, because the boiling of any liquid occurs when its vapor pressure becomes equal to the external pressure. Usually that's done by raising the vapor pressure of the liquid to atmospheric pressure by heating it. But it can also be done by lowering the external pressure until it becomes equal to the vapor pressure of the liquid. At room temperature, this water has a vapor pressure of 22 torr. As a vacuum pump sucks the air out of the chamber, the pressure in the chamber drops. Now the water begins to boil, and yet it is boiling at room temperature. It is not hot water. It's only boiling because the external pressure has matched the vapor pressure of the water in the beaker. When we open a vent and let the air back in, we see that the water will immediately stop boiling.
Well, what if we don't have a vacuum pump, but we climb a mountain, Mount McKinley, where the elevation is 20,000 feet and the air pressure is just 380 torr? Given this table of temperature versus water vapor pressure, at what temperature do you think water will boil on top of Mount McKinley? Here's a slide we talked about before, and it's asking for the substance with the highest boiling point. Which of these three substances, A, B, or C, is going to have the highest boiling point? Now, there's a very useful equation relating vapor pressure and temperature to the heat of vaporization of a substance. It's the Clausius-Clapeyron equation, where we plot vapor pressure versus temperature. And when we plot it in this form, we get y equals mx plus b, and the slope of the line is minus the heat of vaporization divided by r. So if you have a whole set of data of vapor pressures at different temperatures and you plot them, you can get a straight line plot if you plot it in this format, and the slope of that line is going to tell you what the heat of vaporization is. There's a two-point form for the Clausius-Clapeyron equation as well, and the equation right here can be used with just two vapor pressures and two temperatures. It's not as accurate as having a whole series of vapor pressure and temperature data. It can be used to approximate the heat of vaporization of the liquid that you're talking about. And it can also be used to predict the vapor pressure if you know the heat of vaporization and the normal boiling point, right? At the normal boiling point, you know one of the temperatures, and you know the pressure is going to be 760 torr. So you can use that to figure out at another temperature what the vapor pressure is going to be. Scientists use the term fusion to talk about melting. And as a solid is heated, its temperature rises and the molecules vibrate more vigorously. Now, once the temperature reaches a threshold point, the melting point or fusion point, the molecules have enough energy to overcome the attractions that hold them in position in the crystalline solid, and the solid melts or fuses. The opposite of melting is freezing. Well, we've talked about boiling. What happens during melting, or fusion as it's called? As a solid is heated, its temperature rises and the attractions between the particles begin to loosen. The molecules vibrate more vigorously. And eventually you reach a temperature where the molecules have sufficient energy to overcome these attractive forces that are holding them in the crystal lattice, and the solid melts or fuses into a liquid. The opposite of melting is freezing, when a liquid coalesces into a crystal lattice to form a solid. Now, what are these attractive forces that exist between particles of matter? The first, and one of the strongest, is ionic bonding. Here you have a positive ion electrostatically attracted to a negative ion. These are very strong attractions and are the reason that the boiling points and melting points of ionic substances are very high. The crystal lattice energy for ionic substances ranges from 400 to 4,000 kilojoules per mole. That's a lot of energy to break the crystal apart into its ions. Attractive forces between particles can also be covalently bound compounds, which are polar. And here, the positive end of a polar molecule is attracted to the negative end of another polar molecule. This kind of energy or bond is an intermolecular attraction, and the energy ranges from 5 to 25 kilojoules per mole, quite a bit less than the electrostatic attractions in an ionic crystal. Much lower boiling points and melting points than ionic substances, and these tend to be soluble in polar solvents as well. Now, dispersion forces exist in all molecules, and dispersion force is another way of saying a temporary induced dipole. When you have an electron cloud around a molecule, the electrons aren't static, they're always moving about. And at any one given instant, they may be more over to one side than another side. And at that instant, the side with the higher electron density is going to be negative, and the side with the lesser electron density is going to be positive. And this can induce a dipole in an adjacent molecule and form a weak attraction. Dispersion forces range in energy from 0.05 to 40 kilojoules per mole. Substances which only have dispersion forces as their interparticle attractions have low boiling points and melting points, and they tend to be soluble in nonpolar solvents. We've already discussed how charge density is related to lattice energy. The higher the charge density, the higher the lattice energy. And what is charge density? It's the charge of the ion, whether it's +1, +2, +3, -1, -2, -3. And that's divided by the ionic radius, which is proportional to the volume of the particle. So the larger the charge, the stronger the attractive force is going to be, because the higher its charge density is going to be. And the larger the ion, the weaker the attraction of that particle to others, and the less its charge density. Well, now let's talk about dipole-dipole attractions. We've already mentioned this before, that you have to have two conditions to have a dipole. You have to have polar bonds, and you have to have an asymmetric or lopsided molecule. And that will give you a permanent dipole. The permanent dipole adds to the attractive forces between molecules. The stronger the dipole, the higher will be the boiling and melting points relative to nonpolar molecules of similar size and shape. So just take a look at this. Here's formaldehyde, its molar mass is 30. Here's ethane, its molar mass is 30. And as far as the boiling point goes, the boiling point of formaldehyde is minus 19.5 degrees Celsius, and the boiling point of ethane is minus 88 degrees Celsius. Much, much, much lower. So they have exactly the same mass, but the boiling point of formaldehyde is much higher. Why? Because formaldehyde is a polar molecule. It has this very electronegative oxygen, which draws the electron density towards it. This side of the molecule becomes negative, the bottom side becomes positive, and it can attract other formaldehyde molecules with this dipole-dipole attraction. Ethane, on the other hand, is a nonpolar molecule. The only thing it has going for it is dispersion forces, which are much weaker than dipole-dipole attractions. Take a look at bromine with a molar mass of 160, or iodine chloride with a molar mass of 162. So approximately the same molar mass, and yet the boiling point of bromine is 332 Kelvin, and the boiling point of iodine chloride is 370 Kelvin, a bit higher than 332. It's harder to boil iodine chloride than bromine. Why is that? Iodine chloride is a dipole, a permanent dipole. Chlorine is more electronegative than iodine. So you have a permanent dipole here, and iodine chloride can attract another iodine chloride molecule, form an attraction, which makes it harder to vaporize the substance because those attractions have to be broken. Bromine, on the other hand, is a nonpolar molecule, completely covalent bond, and again, the only thing going for it is its dispersion forces, where the electron cloud shifts from one side to the other, forming a temporary dipole. So here's a slide that shows a relationship between dipole moment and boiling point. And we can see that the higher the dipole moment, the higher the boiling point is. The dipole moments are light blue. We see as they go up, so does the boiling point, which is the column in yellow. This is because the molecules become stickier as their dipole moment increases. The attractions between particles increases, and it becomes harder for molecules in the liquid phase to break away and jump into the vapor phase. So in class, I'm going to show you a number of slides like this, where you have to select the substance in each pair with the higher boiling point. Let's do this slide together here. Okay, between number 1, which is called 1,2-difluoroethane, and this one, 1,1-difluoroethane, which one do you think would have the higher boiling point? Well, the answer to this one is going to be number 2. And the reason is that both fluorines are on one side of the molecule. Fluorine's the most electronegative element, and therefore there's a real asymmetry to the molecule. It's lopsided, and the negative side of the molecule is the side with the fluorines. In number 1, the fluorines are distributed on each carbon, and you don't have that lopsided nature, and you don't have a molecule with as strong a dipole as number 2. So now let's look at 3 and 4. Which one would have the higher dipole and therefore the higher boiling point? And again, the answer is number 4. Cis-dichloroethene is the name of it. This is trans-dichloroethene. Cis-dichloroethene has both of the highly electronegative chlorine groups on one side of the molecule. It's more lopsided than number 3. Therefore, it has higher dipole moment and a higher boiling point. Now, hydrogen bonding is an especially strong type of dipole-dipole attraction, and it occurs when hydrogen is bound to either oxygen, nitrogen, or fluorine. These are the most electronegative atoms, and when bonded to hydrogen, they strongly pull the bonding electrons away from hydrogen towards oxygen or nitrogen or fluorine. So the deshielded proton of hydrogen is strongly attracted to the electron cloud of a neighboring molecule. So to give you an example, non-hydrogen bonded dipoles have a bond strength of between 5 and 25 kilojoules per mole. But hydrogen bonded dipoles have hydrogen bonding from 10 to 40 kilojoules per mole. And just for reference, a normal covalent bond is around 150 to 1200 kilojoules per mole. Now here's a question. Which compound does not break the trend of its group? I want the compound. After you examine the slide, you will see a compound which is acting unlike the others in the other groups and maintaining the trend of its group instead of spiking. And can you tell me which compound that is of these four? And more important, can you tell me why that compound is not spiking like the others are spiking? Now let's review some questions that I plan to ask you in class. Here you have four compounds. Which of these compounds engage in hydrogen bonding? 1 and 4, 3 and 4, 2 and 3, or 4 only? Be ready to answer that in class. And for this one, select the compound in each group that has the higher boiling point. Of compounds 1 and 2, which one has the higher boiling point? Of compounds 3 and 4, which ones have the higher boiling point? And here's another. Again, between 1 and 2, which one is a liquid? The other one's a gas. And between 3 and 4, which one would be a liquid? The other one would be a gas. Can you identify those? Now, the one type of interparticle attraction we haven't talked about is dispersion forces. And as we mentioned a little bit before, temporary instantaneous dipoles is what dispersion forces are. And it's caused by the electron cloud shifting. It's a weak interparticle attraction common to all molecules and atoms, but the ones which have ionic or dipole attractions have so much stronger attractions that dispersion forces are negligible. So it's the default for molecules which have neither ionic interparticle attractions or dipole interparticle attractions. The way it works is the bigger the particle, the bigger the electron cloud. In other words, the more its molar mass, the more electrons you have, and the more shiftable that electron cloud is. The more it can flip back and forth, and that will cause stronger dispersion forces. So here's an example. At any given instant, a molecule might have its electron cloud shift in one direction. That makes that side of the molecule negative and the other side positive, and that will induce a dipole in an adjacent molecule because the electrons will be attracted to that positive side of the molecule. And you'll have a weak attraction between these two particles. At the next given instant, it can just as well flip back. And so the thing to note is that these are temporary attractions that are dependent on the size of the electron cloud. The magnitude of the induced dipole depends on several factors in dispersion forces. First, the polarizability of the electrons. In other words, the volume of the electron cloud. So as we mentioned, the larger the molar mass, the more electrons. The larger the electron cloud, you'll have increased polarizability and stronger attractions. The other thing to note is the shape of the molecule is a factor. More surface-to-surface contact means a larger induced dipole and stronger attractions. Well, in terms of molecular size, here you can very readily see a trend in the noble gases. Helium's the smallest, xenon is the largest. Helium has the smallest polarizable electron cloud. It's only got 2 electrons. And xenon has many more electrons, the molar mass of 131. The boiling point for helium is 4.2 Kelvin. The boiling point for xenon is 165 Kelvin. Here's another trend. The alkanes, you have pentane, C5H12, hexane, C6H14, and so forth. And you can see a direct correlation between molar mass and boiling point. Again, that has to do with the polarizability of the electron cloud N-nonane has stronger dispersion forces than N-pentane because it has a more polarizable electron cloud around it. The shape of the molecule is a factor. Here you have two isomers of pentane. One is in a long chain, the other is in a ball. It's exactly the same molar mass. You've got the same number of carbons and hydrogens in both, but their structures are different. But just compare the boiling points of the two. The N-pentane, the one in a long chain, has a boiling point of 36.1 degrees Celsius. The one in a ball has a boiling point of 9.5 degrees Celsius. So why is the long chain one have a higher boiling point? Well, it's got stronger dispersion forces. Because of its shape, it has more surface area involved in the induced dipole, involved in the attractions between the two particles, compared to the spherical one. And because of its shape, it has stronger dispersion forces and therefore a higher boiling point. Well, here's another one I'll ask you in class. Choose a substance in each pair with a higher boiling point. Methane or N-butane. And for this pair, both with a structure C6H12, one is in a long chain, the other is more spherical in its shape. So now we're going to look at the steps involved when we take ice below 0 degrees, ice at minus 25 degrees, and add energy to it, add heat to it, until we transform that into superheated steam at 125 degrees Celsius. There are 5 distinct steps and 5 distinct calculations that have to be made to get the total energy in this transformation. The first one, you start at ice at minus 25 degrees and you warm it to 0 degrees because the ice can't melt until you get it to 0 degrees. For that transformation, you use the specific heat of ice, 2.09 joules per gram delta degrees C. That will enable you to calculate the heat involved in getting the ice up to 0 degrees Celsius. The second step is to melt all of the ice. And note there's no temperature change in this transformation. It's at 0 degrees when it starts melting, it's at 0 degrees when it finishes melting. So for that we use the heat of fusion of ice, 6.02 kilojoules per mole. Notice there's no delta degrees C because there's no change in temperature when we have a phase change. Finally, we get all of the ice melted to water at 0 degrees C, and we add more heat to it. And what does that do? It increases the temperature of the water. And we have to increase the temperature of water to 100 degrees before we can get the water boiling. So, again, we use a specific heat, the specific heat of water, 4.18 joules per gram delta degrees C. When we get to the boiling point, we need to add more energy to get the water to vaporize from liquid water to gaseous water. So here's water boiling to steam. Again, note there's no temperature change. It occurs at 100 degrees Celsius. And for this transformation, we use the heat of vaporization of water, 40.7 kilojoules per mole. Again, there's no delta degrees C because there's no change in temperature. The last step is when we have steam at 100 degrees and we want to warm it to steam at 125 degrees. For this we use the specific heat of steam, 2.01 joules per gram delta degrees C. And that will actually bring the temperature of the steam beyond 100 degrees to 125 degrees. So let's look at each one of these calculations. The first one, we use the specific heat of ice, 2.09 joules per gram delta degrees C, times the 18 grams of mass of the ice, times a temperature change of 25 degrees C. So that's 0.94 kilojoules. The second step is to melt the ice using the heat of fusion of ice, 6.02 kilojoules per mole. We have 1 mole of it, so that's 6.02 kilojoules. Third step is heating the water from 0 to 100. That's 4.18 joules per gram delta degree C. It's specific heat times the mass times the temperature change from 0 to 100, and that's 7.5 kilojoules. The fourth step is to boil the water and convert it into steam. So for this step, we use the heat of vaporization of water, 40.7 kilojoules per mole. And we have 1 mole of it, so that's 40.7 kilojoules. The last step is to superheat the steam at 100 degrees to steam at 125 degrees. We use the specific heat of steam, 2.01 joules per gram delta degree C, times 18 grams times a temperature change of 25, from 100 to 125. So that's 0.9 kilojoules. Note the biggest energy absorption is step number 4, boiling the water. Water has a very high heat of vaporization, and it requires much more energy than any of the other steps to boil away this 1 mole of water.